Hello, my name is Justin Kerns, and today I will be speaking to you about the ODOT Research Project, Soil Amendment for Stormwater Volume Reduction. The research team consisted of MS consultants. We were the principal in charge and the principal investigator. The United States Geological Survey, USGS, served as the co-principal investigator, responsible for flow monitoring and hydrologic analysis. Stone Environmental was responsible for soil amendment plans and report assistance. And Buds Inc. served as the general contractor responsible for soil amendment installation and construction. Research objectives. ODOT wants to avoid having to purchase additional right-of-way for large post-construction stormwater detention BMPs. It's expensive and increases the project footprint. The Ohio EPA and ODOT both allow for underground detention and manufactured systems, but they're not preferred. These systems are expensive to construct and often expensive and difficult to maintain. So ODOT wanted to develop additional options for managing post-construction stormwater quantity on transportation projects. The goal is to provide a low-impact, cost-effective alternative stormwater BMP that could be sited in the ample available green space along uncurbed roadways, which is currently underutilized. The concept for the new BMP is soil amendment. By amending the top few inches of native soil with higher infiltrating and nutrient-rich materials, we can increase initial abstraction, infiltration, and evapotranspiration, reducing runoff from roadways before it enters storm sewers, creeks, and rivers. This prospective BMP would also benefit ODOT in terms of off-site mitigation potential. As demonstrated by the image on the right side of the screen, narrow impervious corridors don't provide a lot of opportunity for stormwater management, except for underground detention or manufactured systems. These areas are hard to treat. However, the area to the north has a nice wide grassed median that could provide more cost-effective stormwater treatment. This is what this prospective BMP aims to take advantage of. The research project kicked off in May of 2017. We conducted 1 year of existing conditions flow monitoring, which ran from March of 2018 to March of 2019. Monitoring was suspended during winter months because the snow and ice interfered with collection of runoff data. I'll cover more detail on the flow monitoring setup and equipment in the next few slides. But essentially, we wanted to establish a baseline and determine how much runoff is occurring along typical ODOT roadways currently. Then we installed various amended soils, which again, I'll cover in more detail in the next few slides. After the amendments were installed, we conducted over 1.5 years of post-amendment flow monitoring to see what impacts the soil amendments had on runoff quantity. We found sites across the state of Ohio that were ideal for flow monitoring. Criteria consisted of grass shoulders and side slopes, all within ODOT right-of-way. We looked for areas that were generally consistent with the current vegetated filter strip BMP used by ODOT, wide, grassed, shallow slopes that receive sheet flow from the roadway. We found that medians provided the best location due to the controlled drainage area. There was no contributing drainage area from outside of ODOT right-of-way, and a high percentage of the flows came from paved roadway surfaces. We chose wide medians that provided ample safety for installation and maintenance crews, and we also looked for areas with guardrail to protect the equipment and crews. Distributing the sites across the state allowed us to capture a variety of rainfall patterns. We ended up selecting 12 monitoring sites across the state, 4 along State Route 161 and State Route 16 between Columbus and Coshocton, and 8 sites on US 30 between Bucyrus and Canton. 2 of these sites were control sites, which did not have any soil amendments performed. The control sites were co-located next to another site that was amended, as you can see on the map. BMP Site 2 and Control 1 were co-located, and BMP Site 7 and Control 2 were co-located. This allowed for direct comparison of runoff between an amended site and non-amended site. The control sites also helped identify any major environmental or rainfall changes between the two monitoring periods and helped isolate runoff variables during data analysis. This picture shows the monitoring equipment setup installed at each monitoring site. Rainfall was captured in the rain gauge and measured. Flow rate was captured and measured through an H flume, which was installed in the ditch line just upstream of the existing catch basin to capture all flow coming off the roadway. Wing walls were installed to prevent flow from bypassing the measuring equipment. During periods of runoff, data and photos were collected at 1-minute intervals and transmitted to USGS via cellular data. And all the equipment was powered by solar panels. The research team evaluated numerous natural and manufactured soil amendment materials with the intended goal of improving the soil porosity, texture, and capacity to hold moisture in order to improve the soil's long-term capacity for infiltration and exfiltration. The team decided that sand, expanded shale, and compost would be the best to install for field testing. It came up with 4 different amendment designs: compost and sand at 4-inch depth, compost and sand at 6-inch depth, compost and expanded shale at 4 inches, and compost and expanded shale at 6 inches. For those that don't know, expanded shale is formed when shale is crushed and fired in a kiln. This process causes tiny air spaces in the shale to expand. The idea was that the sand or the expanded shale would provide infiltration and moisture capturing benefit, while the compost would provide vital nutrients and organic content to maintain robust vegetation, which will also aid in runoff reduction. These images show the general construction procedure of the soil amendments. We rip the soil to loosen it up, then remove the top few inches to make room for the amendment material. We placed our amended materials and then rototilled it to incorporate the amendments into the native soil and create a homogeneous soil layer. Then we applied a compost blanket, seed, and erosion control mat to reestablish the vegetation. We also left the bottom of the median swale undisturbed because we wanted to measure the effects of the soil amendment on the sheet flow across the side slopes, not the impacts of the soil amendment on the concentrated flow in the ditch. This picture shows the monitoring sites immediately after the soil amendments were constructed in March of 2019, and then a few months later in June 2019, after the vegetation had reestablished. We began the data analysis portion of the project by first determining what an event was. We defined a rainfall and runoff event as beginning when the first 0.01 inches of rainfall was recorded, and it ended when the measurable rain and runoff both had ended for at least 3 hours. The events were divided into 2 periods: a pre-BMP period, which occurred before the soil amendments were installed, and a post-BMP period, which was after the amendments were installed. This graph shows an example of an event. You can see in the pink line measuring the cumulative rainfall in inches, and you can see when the rain starts and when it ended. And then you can also see in the blue line when measurable flow was first recorded and when flow or runoff ended. That flow is measured in the flumes in cubic feet per second. This next example shows an event in which runoff did not occur. So the pink line still shows the cumulative rainfall in inches. You see when the rain started, when it stopped. However, you see that no flow was recorded in the flume. Because it was such a small rain event, it did not result in any measurable flow. The main metric we looked at during data analysis was the runoff volume as a percent of rainfall volume. So we took the total amount of rain that fell across the site and compared it to how much runoff was actually generated and measured in the flume. And this is what we called runoff percentage. In total, we recorded over 4,200 individual events over the monitoring periods. For each of these events, we computed event duration, total rainfall, rainfall intensities, the max rainfall intensities for 1, 10, and 30-minute intervals. We also recorded the total amount of rain that had been received within the previous 24, 48, and 168-hour periods in order to evaluate the antecedent conditions and the results on runoff. We also looked at the total runoff and runoff percentages for each of these events. So one of the main questions we asked was, did event runoff percentages change from pre-BMP to the post-BMP periods? So what we saw was that the total runoff percentage varied appreciably between sites, even in the pre-BMP period. We saw that total runoff percentages did not decrease in the post-BMP period at all the sand or all the shale amended sites. And 3 out of the 4 BMP sites with the largest decrease in total runoff percentages were amended with sand. This graph here, if you look at the lines highlighted in red, those were the sites that saw a decrease in runoff volume percent. But generally, the results were pretty mixed. And another observation was that the pre-BMP runoff percentages were much lower than we expected going into the project. This graph shows the runoff percent by sites. This includes all events, even those that did not result in any runoff. So as you can see, only a little more than 1/3 of events actually resulted in any measurable runoff. So then we took the same data set and we removed all the sites that didn't result in runoff so that you could get a better appreciation for when runoff occurred in the pre-BMP period compared to the post-BMP period. And again, you see a mix of results. Some sites saw a decrease in runoff volume, others saw an increase. So the next question, were there any changes in rainfall characteristics from the pre-BMP period to the post-BMP period that might explain any of the observed changes in runoff percent? And this graph here shows a rainfall distribution for all the rainfall events recorded at each separate monitoring site. And as you can see, the rainfall distributions were all fairly even between the pre-BMP and the post-BMP monitoring periods. Therefore, we don't believe that rainfall characteristic had a significant impact on our results. It was all very consistent statistically between the pre and the post amendment periods. So some of the key takeaways from our results: the pre-BMP runoff was lower than we expected. The post-BMP runoff was, again, even a little bit lower than that, although not as significant as we had hoped for. Sites with the higher pre-BMP runoff percentage generally saw a higher reduction than sites with the lower pre-BMP runoff. And sites with lower pre-BMP runoff essentially had little room for actual reduction to be measured. Because they were already so low in the pre, there was not much room for them to go down in the post-amendment period. We saw a little difference between the performance of the sand and the expanded shale. And we saw a little difference in performance of a 6-inch amendment compared to a 4-inch amendment. Rainfall and environmental factors also don't appear to have caused a significant impact between the two monitoring periods. So therefore, MS consultants made recommendations to ODOT. Based on our data analysis, we recommended that the amended vegetated filter strip, AVFS BMP, be added to the ODOT location and design manual as a water quantity BMP. Amending the existing soils provided soil quality benefits. We saw increased organic content, increased nutrients, increased homogeneity of the top layer of soil. It is a space efficient BMP that utilizes the grass medians and side slopes along ODOT roadways, and it can be incorporated into existing ODOT right-of-ways without the need to acquire property. The amended vegetated filter strip is low maintenance. It doesn't require anything more difficult than what ODOT is currently performing on the existing shoulders and medians. It just consists of routine mowing and looking out for rills and other signs of erosion. So while we didn't see a large reduction in stormwater runoff volume, we still saw a slight reduction and low runoff in general, lower than expected. The average post-amendment runoff percent was less than 25%, and the maximum runoff percent that was observed at any site after the amendments were installed was still only 37%, so very low runoff percentages. Therefore, by constructing the soil amendment, we can, at the very least, increase the likelihood that runoff will be low. And the research team conducted cost-benefit analysis and found that the amended vegetated filter strip BMP is cheaper than traditional stormwater BMPs currently being used by ODOT. I'll explain this in more detail shortly. The amended filter strip is also easy to construct, both for redevelopment projects and for new construction. MS consultants recommended the following design standards. More details will be available in the ODOT location and design manual, but the general guidance calls for limited compaction. This involves passes with a smooth drum roller. The intent is to compact the soils enough to provide adequate vehicle safety. We don't want to create any turnover risks in the event of a vehicle tire were to leave the roadway. And we want to provide a stable enough surface for emergency vehicles to cross the median, as well as for ODOT maintenance equipment, tractors and mowers to operate as they currently do. The general amendment construction procedure is similar to how we installed them during the testing phase. We'll rip the soil and excavate. We'll add the sand and compost amendment materials. We'll rototill, compact it, apply compost blanket, seed, and erosion control mat to stabilize. Here are some additional design standards the MS consultants recommended to ODOT. Again, more details will be available in the ODOT location and design manual. But in general, the guidance calls for a 2-foot minimum from the edge of paved shoulder, 2-foot minimum spacing from the toe of the slope or ditch bottom, a 4-foot minimum width for the amended vegetated filter strip, 3-to-1 maximum slopes. All runoff must sheet flow to the amended vegetated filter strip, and a minimum 70% grass coverage must be maintained within the AVFS, as well as all contributing permeable areas to the filter strip. Here's an example of the standard construction detail being developed by MS consultants. This will be revised and included in the ODOT location and design manual. But in general, we show the amended vegetated filter strip installed parallel with the roadway so that it can capture sheet flow directly from the pavement. The amended filter strip will stop before the toe of the slope, so it will not extend into the ditch bottom. And we are creating construction steps that correspond to the pictures we reviewed a few slides ago. Like I mentioned before, maintenance is minimal and consists of routine mowing and inspection for rills, gullies, other signs of erosion. This maintenance is much less than traditional stormwater quantity BMPs like detention ponds, bioretention areas, and it's substantially less than underground or manufactured systems. The research team conducted a cost-benefit analysis for the amended vegetated filter strip, and we found that the construction process and materials had a lot of overlap with the materials and procedures of a typical ODOT roadway project. This results in a tremendous cost-sharing potential. The geometry of the amended vegetated filter strip is the same as a typical grass side slope and is seeded with the typical ODOT grass seed mix. And the erosion protection is necessary for all disturbed area. So these items become somewhat negligible in terms of the overall cost of the BMP. There's also no specialized equipment, and other materials are all very easy to obtain in the state of Ohio. Taking all this into account, the cost to treat 1 acre of tributary ODOT right-of-way using the amended vegetated filter strip is about half that of traditional ODOT stormwater BMPs. This does not include the cost to acquire additional right-of-way, which increases the cost efficiency because traditional BMPs would require additional land acquisition. Real quickly, this image shows an example of how the amended vegetated filter strip can be implemented on a typical redevelopment project. In this example, we're looking at a 10-acre disturbed area, all within existing right-of-way. resulting in a 20% treatment requirement. Therefore, 2 acres of ODOT right-of-way need to be captured and treated to meet post-construction stormwater management requirements. Based on the recommendations of MS consultants, the amended vegetated filter strip area itself is given 100% credit, while the tributary area within ODOT right-of-way, like the roadway and shoulders themselves, that sheet flow to the amended filter strip will be credited at 60%. However, the maximum width of pavement that you are allowed to take credit for is limited to the width of the amended area itself. So for example, we call for a 6.5 foot wide filter strip along the road. So while the contributing area for the center crowned roadway is 24 feet, we only take credit for 6.5 feet because that is the width of the amended strip. At 60% credit for the tributary area and 100% credit for the amended area itself, we'll get a total stormwater credit of 2.06 acres, which meets our 2-acre requirement. I will note that this example assumes the crediting system recommended by MS consultants. ODOT and the Ohio EPA are still negotiating the final credit system, and that will be available in the ODOT location and design manual. In summary, ODOT wanted an alternative to underground storage and traditional BMPs that require extensive right-of-way acquisition. The amended vegetated filter strip BMP are located in existing grassed areas along uncurbed roadways that are currently underutilized. They are space efficient, they minimize right-of-way acquisition, they're good for off-site mitigation, they increase the likelihood that runoff will be low, they improve soil quality, and they are cost efficient and easy to construct. If you have any questions, please do not hesitate to reach out to myself or Jon Prier at the Ohio Department of Transportation. The final report will be made available by ODOT for this research project. And the USGS also has a separate published report that goes into more detail on the data analysis portion, available at the link shown on the screen. Thank you.